Hello everyone, and welcome back. Today we're going to be continuing our exploration of dimensionality reduction and discuss a method called linear discriminant analysis. So this is sort of a second part of our little investigation of dimensionality reduction. So if you haven't seen the principal component analysis before this, definitely check that out so you can sort of see the pros and cons and the implementation comparisons of both of these methods, because both do offer the same exact solution but in some sense different ways, and sort of goes about it in different ways. But when I say the same solution, I mean the same reduced data, but it represents that data in slightly different ways because their targets are a little bit different. But generally speaking, their goal is to reduce the dimensionality, but with respect to different metrics. So, firstly, PCA, principal component analysis, is referred to as an unsupervised dimensionality reduction algorithm because it does not consider the Y values, whereas LDA, or linear discriminant analysis, will be viewed as a supervised method because we will assume or take into consideration the Y values associated to the X values of our data. But keep in mind, both are methods for dimensionality reduction, so you might want to use both PCA and LDA in parallel and to compare the values and results to see which one is more appropriate for your particular data set. But regardless of the method that you plan to use, both methods do assume that your data frame or your data matrix are transformable under a linear transform in some sense, if the goal is to create a linear regression model, or they can be linearly correlated to one another without any multicollinearity. Then LDA and PCA would be let's say appropriate metrics. So they can actually be viewed as parametric tests to some degree, or parametric dimensionality reduction algorithms. All right. So those are the first things that you definitely need to understand. So let's go through some of the basic things about PCA that we described. So what was PCA? So PCA's goal was to maximize. So it maximizes the total variance, and finds the directions, which we also call the principal components, which, keep in mind, are eigenvectors of an associated covariance matrix that capture the most variance in the data. Right? Now, linear discriminant analysis is going to be guided by the following question, or I guess goal. Suppose we want to, or we seek to, so we seek to classify data into, I don't know, two or more categories. Right? For example, like in logistic regression. And let's assume that when we perform that classification onto our data, or that might just be how our data is originally presented to us. So this is going to be our original data X. Let's assume that our classifiers sort of look like this, and let's assume our other classifier looks like that. So what LDA is going to try to do is it's going to try to reduce the dimensionality so that our classified data, so it's going to project it to a different domain, such that our data appears more divided or clearly separated in the new realm. Okay, so this would be a clearly separated, or more clearly separated, or transformed data. Right, so it's going to try and maximize that separability between these particular things, and in some sense it's going to try and find some way to linearly divide these particular regions. Okay, so let's formally state what the goal of linear discriminant analysis is. So the goal of LDA. linear discriminant analysis. And one can frame it as follows. So its goal is to maximize the separability by finding the directions, and we're going to be calling those directions the linear discriminants, aka directions, which again will also be eigenvectors that maximize. Actually, that discriminants word doesn't look very clear. Let's write it on a different line. So the linear discriminants that maximize the distance between the means. Some people will also call them centroids of different clusters. And while at the same time minimizing, so what's the main goal? Minimizing the variance within classes. Variance within classes. That's a very important word. So keyword here, within. All right. So let's think about this mean centroid type of thing. So if we look at, for example, our green region here and our pink region here, so the centroid's in some sense the center of those circles. So that's the center for green, and that would be the center for purple. And if you notice, there's that distance between them. But over here, if we look at the centroid for there and the centroid for there, then what you have here is that the centroid distance is actually a lot larger in that particular picture, right? But in some sense, those circles will have smaller area because we might have removed a few of them or reduced the dimension for which that circle or hyperdimensional ellipsoid actually belongs. So in order for us to do this, we need, for example, a classifier, say y1, and another classifier y2 in order to maximize that separability, because we're looking at, for example, a y value. So that means instead of being an unsupervised model, since it requires classifiers, which is of course a categorical variable or a numerical variable that has been discretized, let's say y, that means this method will be a supervised model. So a supervised model. So it's in some sense very different from the principal component analysis dimensionality reduction algorithm. For one, it's supervised compared to unsupervised, and it's looking at maximizing the separability instead of maximizing the total variance that is remaining inside of our data when we actually do reduce the dimension of our data. So let's go and talk about how you're actually going to perform a linear discriminant analysis on your data set. So the first step of an LDA process is going to prepare your data. And before we get into the step-by-step process of how to perform an LDA, it's actually going to be very, very similar to a MANOVA test. So if you've ever done multivariate analysis of variance tests on multivariate equality of mean vectors, you will see a lot of similarities in this approach, which in some sense can be viewed as a motivation of why some of these metrics are defined the way they are. So let's look at, first off, our data matrix X, which, keep in mind, is going to be a n by p matrix. So what we're first going to have is we're going to have our x1 values, our x2 values, all the way down to our xp values sorted within this particular matrix. And let's clearly define those particular columns. Now what you're actually going to do is you're going to partition this with respect to the classes in that data set. For example, this is going to be classifier 1, classifier 2, all the way down to, let's say, classifier D. Okay, so let's assume that we, for example, have M1 values here, M2 values here, all the way down to M values D here. So that means M1 plus M2 all the way down to, say, MD plus all the way down to MD will be equal to M. Okay, so that's going to be our particular object, and keep in mind this is still going to be an n by p matrix. So once you have prepared your data in this particular world, now our goal is to calculate some metrics. So step number 2. So for each class, which in this picture is going to be corresponding to a big row, each of which is going to have M1, M2 down to MD number of entries in them, we're going to compute X bar vector, which is going to be a P by 1 vector, and keep in mind there's going to be D of them, because in some sense we have D big rows, each of size M1, M2 down to MD. So we're going to have a bunch of these average column vectors. So in our world, that would be the column means function. Once we have those means, which are associated to each of the classifiers for our data, we're also going to do the following. So for each class, again, we're looking at the big rows in the picture that I drew. We're going to compute, because we're going to have a bunch of x bar p by 1 vectors in each of those particular rows, we're going to be defining this matrix Sj, which is going to be equal to a sum from I is equal to 1 to mj of your xi minus x bar times x bar I and then minus x bar transpose. Okay, so you're going to do that for each of your values in that particular class. So what we're actually doing is we're going row by row by row by row in each of our big rows, right? So how many of these are we going to have? Again, we're going to have D of them. Some people will call these matrices partial scatter matrices. Partial scatter matrices. So once you have these little Sj matrices, and keep in mind it's a matrix because keep in mind that this is going to be a P by 1, this is going to be a 1 by P, so that means this object here is going to be a P by P matrix. So once we have those baby matrices, then we're going to compute, or we're going to define, and we're going to follow a parallel notation for the same thing we did with MANOVAs. We're going to have SSE matrix, and this is going to be equal to the sum from j is equal to 1 to d of these baby scatter matrices, right? So this is sort of similar to our S sigma E matrix from MANOVA. The only reason I'm not using the same notation here is because this is a covariance matrix. So that's going to be a covariance matrix, and this is what we refer to as a scatter matrix. So it's looking at things that are slightly more different compared to your MANOVA tasks. So this is sometimes also called as our within class scatter matrix, or within class scatter matrix. Okay, so the next metric that we're going to define also is going to reminisce from the MANOVA world is the following. So we're going to define SSM, and this is going to be defined as follows. So it's going to be the sum from j is equal to 1 to d, and then we're going to have nj, so it's the number of entries in each of those dimensions, so I guess that could be your mj, and then we're going to have x bar j minus x bar bar, and then times x bar j minus x bar bar transpose again. So again, for your MANOVA, this is similar to your S sigma M matrix, but instead of a covariance matrix, this is going to be a scatter matrix. And what is this going to be? Take a guess. If you know MANOVA, you definitely should know the answer. So this is going to be our between class scatter matrix. Our between class scatter matrix. So that's actually quite beautiful. We definitely see a lot of similarities here. Okay, so each of these objects, each of SSE and SSM are P by P matrices, and technically you could define another matrix, for example SST, to be equal to the SSE plus SSM, and you might be able to even build some MSE, M, and MST matrices like we did with the ANOVA test and stuff as well. But we have these particular matrices. Now in terms of the interpretation of SST, we don't actually need it here, but I'll leave to you to sort of explore that on your own in case you are curious. Right? So what is the test statistic in like ANOVAs and MANOVAs? So in the ANOVA world, the univariate MANOVA world, our f-test statistic was equal to MSM divided by our MSE. But now sort of like our SSM and our SSE matrices are matrices, so you can't divide by matrices. So obviously, at least analytically, this is actually equivalent to MSE inverse times MSM. So what we're actually going to do is we're going to take this as a guide on how to sort of move on with this linear discriminant analysis. So from the linear algebra perspective for linear discriminant analysis, one can actually come up with that this is actually equivalent to finding the linear combinations of our x's such that the ratio of the determinant of SSM and the determinant of SSE is actually maximized. Keep in mind the determinant of covariance matrices, which technically is the product of the associated eigenvalues of those matrices, can be viewed as a generalized variance because it's not the trace, it's actually the determinant. And if you remember some of the test statistics such as Roy, Pillai, and Wilkes from MANOVAs, a couple of them actually use the quotient of the determinants of SSM and SSE, and also the inverses and the determinants and the traces of the products of those two in the calculation of those test statistics, which of course, followed an F distribution. And when we sort of look at this, when we're looking at the linear combination that sort of maximize this ratio, that kind of hints at, it's trying to replicate sort of an F-test type of thing where we're trying to see, okay, what type of value will produce an F-stat, which will be above some F-crit, that's in some distribution. So this problem, at least in the linear algebra world, will be equivalent to solving the problem SSMX, where x is some eigenvector, is equal to lambda times SSE times x. Right? So it's obviously an eigenvalue problem, and equivalently, if we look at this from the eigenvector or eigenvalue perspective again, we can represent this as SSE inverse times SSM times x is equal to lambda x, because we have lambda x there. Right, so we have this matrix right here, which I'm going to call this matrix as A. So we have AX is equal to lambda x, which is our traditional eigenvalue problem. So we just need to find the eigenvalues of A and the eigenvectors of A. So that's going to be the next step of our LDA process. So this is going to be step 6. So our goal is to find the eigenvalues and eigenvectors. And these eigenvectors are going to be called our linear discriminants. Our linear discriminants. Remember, for our principal component analysis approach for dimensionality reduction, the eigenvectors of our standardized covariance matrix were our principal components. And here our eigenvectors of our SSE inverse SSM matrix are going to be our linear discriminants. Right? So we're going to be looking at our eigenvalues of this matrix A and the eigenvectors associated to those eigenvectors. Okay, and then once we have those eigenvalues and eigenvectors, we're going to then sort the eigenvalues from greatest to least, just like we did in PCA, except we're just going to have different eigenvalues now. So we're going to have, again, eta 1 is greater than eta 2 is greater than equal to eta 3 is greater than equal to all the way down to greater than equal to eta p. And those are generated from eigenvalues lambda 1, lambda 2 down to lambda p, but now they're just sorted. They're going to have some associated eigenvectors associated to them. Let's call those eigenvectors v1, v2, v3 down to vp. And then what we're going to do, once we have those eigenvectors, we're going to choose your k eigenvalues that you want to keep. So you can either do, for example, a scree plot analysis or maybe a Kaiser criterion process to sort of figure out which eigenvalues you should keep. And let's assume that we keep k, and obviously k is less than p of them, where k is typically strictly less than p, but theoretically it could be equal to p. So once we have those k eigenvectors generated from those k eigenvalues, then we're going to have our reduced data matrix x, which is going to be equal to x times w. So w again is going to be our transformation matrix, where w will be equal to the eigenvectors. Let's call them again u1, u2 down to uk, where those are going to be a subset of the eigenvectors v1, v2 down to vp, right? And obviously this is going to be a p by k matrix. Forcing our matrix x, keep in mind x is going to be an m by p, that's going to be a p by k, which means that this is going to be an m by k data matrix. So our dimensionality is technically reduced here. So what this transformation is going to do is going to transform our data into our new coordinate system. And keep in mind the eigenvectors are again orthogonal to one another. And what it's going to do is it's going to transform it into a coordinate system such that our data values is as separated as they possibly can be with the variables that you have decided to keep. And that's linear discriminant analysis. Before we conclude this discussion, keep in mind the only tricky part about the implementation for LDA is figuring out those scatter matrices, but if you're comfortable with sort of working around data and, for example, which statements and subsets and if statements and so on, that probably shouldn't be a difficulty for you, right? So once you get those scatter matrices, those SSM and SSE matrices, invert your SSE, multiply it by your SSM matrix, find your eigenvalues, eigenvectors, and then the pretty much same process follows as it did with principal component analysis. So let's sort of summarize some of the things that are similar and also different between PCA and LDA. So what exactly are PCA and LDA? Both of these methods are dimensionality reduction algorithms or methods. And sometimes it can help reduce noise and also reduce multicollinearity amongst many other things, right? So what does PCA do? So obviously it focuses on covariance matrices, whereas linear discriminant analysis focuses on what we call scatter matrices, which is kind of focused on the separability or the classification of those data sets. So PCA finds the principal components, and 2 focuses on finding the linear discriminants. Right? So it finds the principal components, which are technically both eigenvectors, but of different things. In particular, is the eigenvectors of sigma z, the standardized data set, and the eigenvectors of SSE, the scatter matrix inverse, times SSM. Right? So it focuses on eigenvectors, and it chooses the eigenvectors whose eigenvalues sort of follow within the upper threshold of your distribution. And the main difference between LCA and PCA are their goal of focus. Again, it focuses on, for PCA, for capturing variances. So we try and keep as much variation in our data set as possible, even when we remove data points. But LDA focuses more on separability of classes. Separability of classes. Right? So since it focuses on capturing your variances, i.e. it's independent of your y values. That's usually why this method is called an unsupervised method, whereas this is called our supervised method for dimensionality reduction. So those are the main things that you definitely want to keep in the back of your mind. And keep in mind, one method is not universally better than the other. Usually what you want to do is do both a PCA and an LDA, look at the results and see which one is best. But that's how you perform a linear discriminant analysis and analyze your results. Hope you enjoyed this video. I'll see you in the next one. Take care.